Now we are going to see some examples of modules. This is the first one. Let A be a ring and I be an ideal of A. Then I is an A module. Let's see how. Since I is an ideal, it's a subgroup of our ring A under addition, because that's a part of the definition of ideal, and our ring itself is an abelian group under addition. So that's why I also becomes an abelian group, which we need for I to be a module. Now the next thing we want is to have a multiplication where we take one element of I and one element of our ring and we multiply them somehow to get an element in I. So it is that function mu which we need for I to be a module. And we define that function like this. Define mu from A times I into I given by this formula. Mu of A comma x by definition is Ax. Here of course it's understood that A is an element of A and x is an element of I. And what is this product? This is just the product of A and x in the ring A. And because I is an ideal and x is coming from I, so this Ax again belongs to I and also is a unique element in I for this A and x. So that's how we have a unique multiplication of elements of I by elements of the ring A. And now we will go and show those other conditions that must be satisfied for I to be a module. It's already an abelian group. Now we have this multiplication also, so we need to verify those other axioms. And for that we first choose two elements, any two elements A and B in our ring A, and two elements x and y in our ideal I, and consider this product A times x plus y, a ring element times the sum of these two elements from the abelian group I, which equals Ax plus Ay. This is one of the axioms in the definition of a module. How exactly is it coming? Well, it's just the left distributive law that you have in the ring A, because ultimately these elements A, x and y are elements of our ring A. So from left distributive law we have this. Similarly, by the right distributive law we also have this. A plus b times x equals Ax plus bx, where this time we are adding two elements of the ring and with that we are multiplying an element x from I. So this is another axiom that has also been verified. And then we have this third one also, AB times x equals A times bx. Where is this coming from? This is nothing but the associative law for multiplication that we have in the ring A. And finally we have this one also, 1 times x equals x, where 1 is the identity element in the ring A. Where is this coming from? Well, this is just the fact that this product is nothing but the multiplication we have in the ring A, and 1 is the identity element, so 1 times anything is that thing. And that is why our ideal I is an A module. So that means any ideal of the ring A is an A module. In particular, A itself is also an A module because that's also an ideal. Next, example 2, which is a special case of example 1. Say in place of a general ring we have a field K. Let K be a field. Then K modules are nothing but K vector spaces over K, and vice versa. Any K vector space is also a K module. And there is actually nothing to see here. I mean, the two definitions they are identical already, right? The only difference between a module and a vector space is that in a module those scalars, if we call them scalars, come from a general commutative ring with identity, whereas in a vector space they come from a field. So if that ring is already a field, then we are getting vector space, that's it. Next, example 3, let G be an abelian group, then G is a Z module, where Z is the ring of integers. Let's see how. Because we are already starting with an abelian group, so we have that. There is nothing to show there. So now all we need is to have a multiplication of elements of the group by integers, that means by ring elements, that will satisfy those other 4 axioms. And that multiplication we define like this. For any integer n and any group element g, by ng we mean this integral power of g, where the exponent is n, which is something we already know from group theory. We know what this means. This itself is partly defined depending on the sign of n. If n is positive, then this is defined recursively. For example, say you define g to the power 1 to be just g. Okay, that's how you define these things in group theory. And then say you have defined g to the power n for some positive integer n, then g to the power n plus 1 is by definition g to the power n times g. And if the exponent n is negative, then g to the power n is by definition the minus nth power of g inverse. Minus n is then positive, which you have defined just now using this recursive definition. So that's how you have this defined for all integers n. So by ng we mean this. Now will this give us the multiplication that will satisfy all those 4 axioms? Let's see. To verify those 4 axioms, we take 2 ring elements, that means 2 integers n and m, and 2 group elements g and h. Alright. So let's see the first axiom first. N times g plus h. This calculation will look very confusing, okay? So we need to really go slowly and see what each step means. What is this plus? This plus is the binary operation we have in g. Alright. Now by the definition of this product, n times g plus h is the nth power of g plus h. But then suddenly in the next step, why did I write gh? This looks like multiplication. Well, the thing here is that this is the binary operation in g. Here I have chosen to not write the binary operation. That's it. Okay. But this is still the same thing. G plus h and gh mean the same thing in this context. Why did I write like this though? That is to remind you of something that we have already seen in group theory. When the group is abelian and you have the nth power of a product like this, then that equals the nth power of g times the nth power of h. This does not happen in a non-abelian group. And then we bring back that name or that symbol for the binary operation in g. This really means g to the power n plus h to the power n. And this is ng and this is nh. So ring element times group element plus group element equals ng plus nh. So the first axiom has been verified. It is true. Next we have the second axiom. N plus m times g. What is this plus now? This is the ordinary addition of integers. And by the definition of this product, this is the n plus mth power of the group element g, which equals the nth power of g times the mth power of g. What is this? This is one of the laws of exponents which you have in groups. Okay, in any group this is true. Regardless of what n and m are, they may be positive, negative, anything can happen. Still this is true. You will find a proof of this in group theory, in the beginning itself. And now, because the group operation is also written plus, so this is really g to the power n plus g to the power m. And then this is ng and this is mg. So you have the second axiom also verified. And next we have the third one, where we consider nm times g. This nm is the ordinary product of the integers n and m. By definition, this is the nth power of g. Now in place of nm you can also write mn because ordinary multiplication is commutative. Now from here, how are we getting this one? This is the other law of exponent. One you used there, this is the other one that we always have in any group. Here also does not matter what the signs of the integers n and m are, any integer works. So that's how you have this. Now this to the power n means n times g to the power m. There was actually no need for this set of brackets, but anyway, and this g to the power m is itself mg. So that's how you have the third axiom also verified. And finally we consider 1 times g, where 1 is the integer 1. By definition of this product, this is the first power of the group element g, which by definition of integral powers is equal to g. So that means the fourth one is also verified. That is why every abelian group is a Z module. And conversely, if you have a Z module, then obviously by definition of modules, it's an abelian group. So abelian groups and Z modules are synonymous. Next we have number 4. Let K be a field and let V be a Kx module. What is this ring Kx? This is the ring of polynomials in the indeterminate x where the coefficients come from the field K. Then V is also a K vector space with a linear transformation. How? You just note this simple fact. Since V is a Kx module, V is also a K module. If instead of multiplying the elements of V by general polynomials, you multiply them by constant polynomials, in other words, the elements coming from that field, then also all the module properties are already there. So that is why V becomes a K module. But as we saw earlier, that any K module is a vector space, a K vector space. So that's how V becomes a K vector space. However, what is this linear transformation? Where is that coming from? You define a function t from V into V by this rule. T of V, this small v is a vector coming from the vector space V. T of V by definition is this product xv. What is that product, however? It is that product that we already have in the module V. Because this is a Kx module, so you can multiply any element V of V by a polynomial coming from Kx. In particular, you can multiply V by x also. So this will then be a unique element again in V, because we have module multiplication with us. So that is why t becomes a well-defined function. Now this will be a linear transformation. To show that t is a linear transformation, we take any two vectors u and v in our vector space capital V and any scalar a in the field K. Now let us first show that t respects vector addition. So we calculate t of u plus v. By definition, that is x times u plus v. Now using one of the module axioms, this equals xu plus xv. However, xu is t of u and xv is t of v. So that's how t respects addition. And for scalar multiplication, we next consider t of au, where u is a vector and a is a field element coming from the field K. So by definition of t, this is x times au. Now note carefully that this a is a constant polynomial and this x is a linear polynomial. Both are polynomials after all. And this u is a module element. So using the third module axiom, this equals xa times u. However, multiplication of polynomials is commutative. So xa is also ax. And then you again use that third axiom to get this one from this one, a times xu. Xu, however, is t of u. So that's how you see that t also respects scalar multiplication. and that is why T is a linear transformation. Conversely, suppose V is a K vector space where K is some field of course, and we also have a linear transformation T from V into V. Then V is a Kx module, so it's in the other direction. But how exactly? What is the module multiplication? We understand one thing, that since V is a vector space, V is already an abelian group. Now we need a multiplication of elements of V by polynomials coming from this ring so that it will get a module structure. What is that multiplication? We define that multiplication like this. For any vector V and any polynomial f of x, which say looks like this, I have deliberately not shown the variation of this index I of summation because it will vary from 0 to some non-negative integer. That's understood. Okay, simply I have written summation. I did not want to write this I also, but then it would look a little strange. Of what? Aix to the power I. I mean, instead of writing the polynomial fully, I have used summation notation, that's all. For this vector V and this polynomial coming from the polynomial ring Kx, we define this product, product of fx and V, like this. Summation ai t to the power I. This t is that linear transformation. So this linear combination of powers of t, where the scalars of course come from the field K, is itself a linear transformation that we have applied on V, which itself means this. This is a linear combination as well of these vectors. T to the power I of V is a vector in our vector space capital V, where you do understand what this ith power of T means. It means applying I copies of T to V. That's what it means. So this is again a vector, this entire thing is again a vector in V. So that's how we get a product of an element of the vector space by an element coming from this polynomial ring, and that is again an element in the vector space. And this product gives V a module structure. It becomes a Kx module. The verification of those 4 axioms for this product I am leaving to you. There is another example also. That example, however, for some reason, it involves non-commutative rings, group algebra, representation, something. So I am skipping that. Okay, I don't know why the authors chose that here. Maybe there is some reason. If we need it later on, we are going to see it. Okay, but now I won't see it. In the next video on commutative algebra, we are going to see how we can define homomorphisms of between two modules, which are both modules over the same ring, and then the other ideas which naturally come after homomorphism will also be seen.